Hello everyone. I'm Jun. In this talk, I'm going to talk about Quasi-Newton methods in preCICE for bounded variables. Yes, so before I go into that, I'm first to go through the Quasi-Newton methods in preCICE. I think, during the course or during the previous talks from other developers or from Philip's talk, you have know quite a bit about the acceleration methods in preCICE or the Quasi-Newton methods. And luckily, I'm talking about same family of Quasi-Newton methods as Philip do. So in preCICE, what we want to do in the implicit coupling case is that we want to solve a fixed point problem where the operator is a combination of the multiple subsolvers. And if you look at the cotton on the right-hand side, we see a fluid solver and a solid solver and an acceleration block at the bottom. So every iteration, in every iteration, you give some input to the two solvers and you get output. This output will be post-processed by the acceleration methods, depending on what you choose. And this will give a new input for the next iteration for the solver, like the fluid solver here. The motivation that we have included Quasi-Newton methods in preCICE is that the fixed point iterations can converge relatively slowly by strong coupling. So in the course, I think you have tuned the coupling strength of the perpendicular flap in fluid case so that you can say by strong coupling, you would need implicit scheme, you would need other acceleration methods to make it actually converge and converge faster. The limitation while choosing the different Quasi-Newton methods is that we have very limited data because we try to treat the solvers as black boxes, so the only data we can use are the sequence of the iterations and residuals on the interface. And the idea here is that we would approximate the inverse of the Jacobian from history of the residue to accelerate the convergence. And this we have also seen in the previous talk. And in preCICE, there are two big kinds of types of Quasi-Newton methods are implemented, which is IQ&ARS and IQ&AVG. They have actually they belong to the same family, which is multi-second Quasi-Newton methods family. And the idea there is that we want to get an approximate of the inverse Jacobian from the second condition. And the V and W here are the matrices of the differences of residuals between iterations and the function values between iterations. So the size of these two matrices are the degree of freedom on the interface times the number of iterations you have from history, which means it has way fewer columns than rows. So this is an underdetermined problem, and for that we combine two minimization problems with it so that we can get a determined approximation of the Jacobian implicitly or explicitly. And in ERS or EMVG, we have two different minimization strategies. And after we get this approximation of the inverse Jacobian, we can use it to calculate update and start the next iteration. And what you see, and I think in the tutorials, it's also very often that you see these methods are used. Here I pick a part from the configuration file in the case breaking down in 2D. It's quite easy that you only need to give the data you want to use to calculate the update, which means the factors that will construct the rows of the V and W. And you can choose different preconditioners to balance the magnitudes of different variables. And you can choose different filter type to keep the, this second problem well conditioned. And you have other settings such as the initial relaxation to start the simulation when you have nothing for Quasi-Newton to handle. And you can choose the maximum used iterations in the past, so which will be the maximum number of columns you can have in V and W, and the time windows you use decide from how many time windows in the past these reuse iterations can come from. And for the MVJ method, I actually only find one case that used it in the whole tutorials, which is not optimal, because it's also a very robust and good method. But here we have similar settings as the S. In addition, we have restart method because in this method we try not to store the inverse Jacobian explicitly. So we have different ways to keep the elements to construct this matrix, but we can't keep all the history. So we have restart methods to like sort out this kind of history periodically. Yes, and for more information on how to use this, how to tune the parameters also, you can refer to Benjamin and Kai Davis and Claudius' dissertation or papers. They have published quite a lot. And I think this is also the methods that people here have used quite often. They are relatively robust. And now what we hope that is that we give the previous points and we get another point. We get a new iterate from it so that we can start a new iteration. And these two figures have shown the relative position of the new point compared to the previous points, depending on where the previous points are and how the shape of how the function looks like, etc. You can do interpolation. You may have a point between the previous inputs or outside, and this can actually lead to a problem sometimes, and this is the overshooting problem that I want to talk about in this talk. So by overshooting, I mean that the Quasi-Newton step can sometimes give values outside the physical bound, because current in preCICE we don't have any place in the configuration where you can tell it that, well, please don't give values outside the bound. This can be problematic with cases, for example, with temperature field, where it should be negative, or with concentration phase, where it should stay in the range of 0 and 1. The concentration field appears quite often in the porous media field, and that is also the first time where I actually spotted this issue. To visualize this overshooting problem, I solved this quite simple equation system with only 2 variables. So what I do is I do the function evaluation on the right-hand side in one solver, and on the another solver I just copy the value, and then I do Quasi-Newton update. And I compute this fake Quasi-Newton update with this formula, and the inverse Jacobian is approximated by neighboring point to each point. And on the right-hand side, we can see that the function values should actually, the output from the solver will always in the range of -1 to 1. And if I do the update, at the green zone, the next iterate will still be in the bound. And if I do it in the red zone, the iterate will be outside the bound. Luckily, this problem is actually quite well because I started the simulation from in the green zone, and the solution of this problem is at the quite center of the green zone, so it's very easy to solve, and you will not overshoot actually while solving it. So, and I also tried to reproduce this problem with our tutorial cases. During the post session, if you have been to Ishan's poster, you should have seen this similar figure. Here you have a heat conduction problem in a macro scale, and you get the heat conductivity from micro scale simulation at each cell. And in the beginning, the field is uniform, and you have a source at the left bottom corner. During the whole simulation, the porosity should only converge to the range between 0.49 to 0.45. But if I increase the expansion speed in the microscale, which means that the coupling between the two scales will be stronger, I can actually observe the overshooting problem, which is visualized in the right-hand side figure, so that this is the porosity value of this cell, the second cell, in the 7th time step over the iterations. And here you can see that at the beginning or at the end is at a very normal value, and it in the end converges. But in the beginning, it can go to values like minus 0.2, which is not physical. And in the literature, I have only found one case that also have this problem, which is, this paper is in Chinese, so I can't show it here. But there they solve also a heat conduction problem with 3 layers, and there they actually have properties, material property, which is like square root proportional to the square root of the temperature. So they really couldn't have negative temperature. So yes, so this is a valid problem, and we want to find some approaches to prevent this overshooting. The assumption is that the solvers will always give output in a physical bound. This is also one point that I feel skeptical about this paper, because they also have output from the solver which is already outside. And the bound I used for the test also is quite simple. So it's not bound from multiple parts also, it's convex and very simple. The approaches I want to add should at least prevent overshooting, should be very at minimal overhead, and we want to have a modular implementation so that we can use it for every Quasi-Newton method, and we hope to retain the convergence speed, which is still a mystery for the Quasi-Newton methods. And we have some ideas here. I have also visualized them on the right-hand side. So the output of the last iteration is the point which is x tilde at kth iteration, and the output from the Quasi-Newton will be outside the bound. And now we can do different things to put it back to the bound. We can either discard the whole update, and do a fixed point iteration at this iteration, or we scale this step so that we keep the direction of the update but still stay in the bound. We can also project the iteration back to the bound, in which we will change the direction of the update. We can also, the mixed step length is the method which can't be visualized, because what I do is I switch between the fallback method and the scaling step method depending on how far away it overshoots, because my argument is that when it's only a little bit outside the bound, I think the Quasi-Newton is still doing the correct thing, so I cut it back to the border. But if it's very far away, I would directly discard step because the Quasi-Newton doesn't have valid information also. And I compared these methods with toy problems I designed, which is not optimal because it can have multiple solutions. But in these experiments, I tried, they all converge to the same solution, so that is actually comparable. But if you have other ideas about better test problems, please talk with me. So I tried different alpha and beta values and different initial status and compare the three methods that can actually hopefully keep the direction of the update. And in these methods, we can basically say that the mixed methods can work quite well, although it needs me to tune the switching point a little bit. I didn't do this for every problem, but I did do it for this problem in general. And what I also observed is that when the alpha is more dominant than beta, then the fallback method will work better. But when beta is more dominant, then the scaling method will work better. I also collect some results from the heat conduction case. By using different expansion speed, I can change the coupling strength, and by choosing different initial radius of the grain in the microscale, I can actually have microscale problems of different nonlinearities. Here, the general impression is that the fallback method actually works way better. And the only case that the scaling step makes more sense is when the expansion speed is normal and the initial and the microscale problem is very nonlinear. So the feeling would be that when the problem overshoots because the coupling is very strong, then fallback methods will work better. But if it's because the sub-problem itself is very nonlinear or the solution is very close to the border anyway, then scaling method might work better. And the mixed method can, in general, works very well if you have the time to tune it. In summary, the overshooting can be a significant issue in Quasi-Newton methods for physical scenarios, and the performance of the methods I mentioned vary strongly based on the problem and parameters, and I think it needs to be evaluated statistically. And also the methods needs to be refined because I think if I'm going to implement this in preCICE, the fallback and scaling length method can actually be merged into one, which is scaling step, but FB is the one with 0 times a factor. So then we can make this scaling factor configurable in preCICE so that you can choose how much of the step you want to keep depending on the property of your problem. And yes, I missed some tests with real applications. So if you have relevant needs, like you want to, you also meet this overshooting problem, or you want to keep the size of the data that will be post-processed by Quasi-Newton, or similar needs in your applications, please contact me. Thank you.
Thank you very much for your talk, Jun. Are there any questions? Yeah? Okay.
Could you maybe shortly explain how you inserted this expansion speed in the two-scale heat conduction? So was this related to the grain expansion or?
Yes.
Okay. So you actually.
So if I have a larger expansion speed, then the size of the grain will reactive more dramatically to the temperature from the macro scale.
Okay. So like a multiplier to this double well potential or?
Yep.
Okay. Okay. Yeah. Thanks.
Thank you for an interesting talk. So the last method, I didn't really understand what that was. The multiple line search or
Mixed.
mixed?
Yeah. Yes. So I set a threshold value, and when the maximum overshooting distance is lower than this, I will use the scaling step method. Otherwise, I will discard the whole step.
Okay.
Are there any other questions? If not, let's thank Jun again for the talk.